everybody. Today we are going to be talking about geometric sequences. We'll look at how we can represent geometric sequences and how we can use those representations to solve problems. So what exactly is a geometric sequence? Well, a geometric sequence is a sequence with a constant ratio between consecutive terms. So if I were to write the sequence 2, 6, 18, let's see, what would the next term be? 54 and 162. This would be an example of a geometric sequence. And I would know that it's a geometric sequence because to get from the one term to the next term, I'm multiplying by a constant ratio called R. So to get from 2 to 6, I multiplied by 3. To get from 6 to 18 times 3, from 18 to 54 times 3, and from 54 to 162 times 3. This is called a geometric sequence with a common ratio of R equal to 3. Now we have geometric sequences like what we have here, 4, 12, 36, 108, and 524. And the common ratio for this sequence is also 3. But then we also number the terms so that we can keep track. So instead of saying, the number after 18 or what number comes after 54, we call it the first term in the sequence, the second term, the third term, and the fourth term. So we have, kind of looks like an XY chart, but we have the term number and the number of the term. So you will have two equations for geometric sequences, but we'll get into those in just a minute. First, let's just figure out if we have geometric sequences or not. So in example 1, is the sequence a geometric sequence? If so, write a recursive definition for the sequence. So let's just figure out, is it a geometric sequence or not? Well, to get from 1.22 to 1.45, what would I have to multiply by? And if I can't figure that out in my head, I can divide 1.45 by 1.22 to get approximately 1.188524. Then to get from 1.45 to 1.68, if I divide 1.68 by 1.45, I get 1.1586 and so on. These numbers are not the same, so this sequence is not geometric. So I don't even have to write a recursive definition. But example B, where's example B? Here it is. Example B, let's see what's happening here. To get from negative 1.5 to 0.75, if I multiply that by negative 0.5, negative 1.5 times negative 0.5 is 0.75. Multiply that by negative 0.5, I get negative 3.75. And then if I multiply negative 0.375 by negative 0.5, I get 1.875. So yes, this sequence is geometric. And I can say that the common ratio is negative 0.5 or negative 1/2. Now, once we establish that it's geometric, we can write an equation for our sequence. And we have two different ways to write our equation. The first is the recursive, and the next is the explicit. So we'll start off with the recursive right now. The recursive definition is a piecewise function. And what it does is it tells you how the sequence works. So a sub n stands for the nth term. And that means a sub 1 would be the first term. So the way that this first line works, this part a sub 1, if n equals 1, this is telling me if it's the first term. N is the number of the term, by the way. N is the number of the term. So this is telling me if it's the first term, then It's the first term. So pretty much the line tells you what the first term is. The second line gives me a little bit more information. It says a n sub n minus 1. Well, if a sub n is the nth term, then a sub n minus 1 is the term before the nth term. In other words, it's the previous term. And then R is the common ratio. So let's try to write the recursive definition for that first example on example B. So here we've already identified that R is negative 0.5. My first term is negative 1.5. So when I set up my recursive definition or my recursive formula, I know that a sub n, I'm just going to copy down the recursive formula. So when I'm working with the recursive formula, I'm going to substitute a number in for A1 and in for R. So when I write my recursive formula, A1 we know is negative 1.5. And then R, I know to be negative 0.5. So this term will tell me the recursive, this is the recursive formula. Now, what does this do? It says there's a geometric sequence. The first term is negative 1.5. After that, you take the previous term and multiply by negative 0.5. So what I could get from this, I could say, okay, well, that's negative 1.5. To get my next term, I would take this, multiply it by negative a half, and get 0.75. To get the next term, I would take my previous term, which is 0.75, times negative 0.5, and get negative 0.375. And I can do that for as long as I wanted to. Now that's cool, but the recursive formula really doesn't help us find terms that are further on down the sequence. So we have the other option. It's called the explicit formula, and it looks like this. And this explicit definition will generate any term I want in the sequence. So the nth term, I need to use the first term, common ratio, and the number of the term I want minus 1. The n minus 1 is an exponent. So let's go ahead and try to do that with this one. So my explicit definition or explicit formula I'm going to copy down that formula. A sub n equals A1 times R to the n minus 1. For any term I want, I'll take the first term, negative 1.5, times the common ratio, negative 0.5, and I'll raise it to the n, whatever n is, minus 1. Example 2 has us translate from recursive to explicit and then explicit to recursive. So here is the explicit definition. I need to substitute, in order to write an equation for this, I need to substitute a number in for A1 and a number in for R, and then I will have switched over. So let's see, my A sub n equals the first term I find right here in the recursive sequence, 12, a recursive formula, times, this is r, 1/3, to the n minus 1. And this time they wrote the r in front of the previous term. And sometimes you'll see that happen because with multiplication, you can do multiplication in either order. Now, on example B, we're going to go the other way. So I have the explicit definition and I need to write the recursive definition. Here is the recursive formula. And again, I need to substitute a number in for A1 and a number in for R. So A1 I'll find right here. So this part is 6. And then R I'll find in the 1.2 spot. So this number will be 1.2. So 1.2. And there you go. So now we can start to apply our knowledge of geometric sequences to solve some problems. So a geometric sequence can be used to describe the growth of bacteria in an experiment. On the first day, there were 9 bacteria in a petri dish. On a 10th day, there were 3 to the 20th bacteria in the petri dish. How many bacteria were in the dish on day 7 of the experiment? So let's start to write down what we have here. On the first day, there were 9 bacteria. So that tells me my first term is going to be 9. The 10th day, there were 3 to the 20th bacteria. So A sub 10 equals 3 to the 20th. And then the bacteria in the petri dish on the 7th day, that's what we have to find. So we have to find A sub 7. So I'm going to jot down what I know. I know the formula for the geometric sequence is A sub n equals A1 times R raised to the n minus 1. And I'm going to substitute in what I know. I know A1 is 9. R to the n minus 1. Now I know that I want to find something on the 7th day. So I know that n is going to be 7. And I'm trying to find A sub 7 equals 9 times R to the 7 minus 1. Or A sub 7 equals 9 times R to the 6th power. But in order to find this, I need to know what is R. Okay, so then maybe I can use this other information I haven't used yet. I know that A to the 10th is 3 to the 20th. So let's say I started off and said, okay, well, I have A to the 10th is 3 to the 20th. But if I were to use this formula, A to the 10th would be the same as this part of the formula. A sub 1 times R to the n minus 1. And the initial amount of bacteria is still going to be the same, so A sub 1 is still going to be 9. And when I'm looking at the 10th day, I know the n would be 10, so 9 times R to the 10 minus 1, or 9th, equals 3 to the 20th. And hey, now I have an equation that I can use to solve for R. So if I divide both sides by 9, I'll have R to the 9th equals 3 to the 20th divided by 9 is 3874, 204, 89. And then if I want to try to solve for R, I can raise both sides to the 1/9 power. So then R would be 9. So now that I know that R is 9, I can take that information, I can substitute it in back up here, and find out what A sub 7 is. A7 is 9 times, lots of 9s in this problem, times 9 to the 6th. So a sub 7 would be 9 times 9 to the 6th power is 478, 2969. So that means that on the 7th day, $478,2969. So 4,782,969 bacteria were present. Now let's talk about geometric series. So I have if you think of the geometric sequence 1 times 3 is 3, 3 times 3 is 9, 9 times 3 is 27. That would be a geometric sequence. But if I start adding up the terms and finding the sum of all the numbers in that sequence, then I have a series. And so I can calculate, so I could either calculate this sum by adding up 1 plus 3 plus 9 plus 27 plus 81, or I can use this formula for the sum of a finite geometric sequence. And finite means it ends. A finite series. So S sub n is the sum of the first n terms. A1 stands for the same number, R is the same thing, n is the same, represents the same thing. So you'll see sigma notation. Remember that sigma stands for sum. So one thing that we'll need to do is we'll need to write the expanded form, and then we can use the formula from before or evaluate this in our calculator to find the overall sum. So when you see this symbol, you read it out loud, the sum from n equals 1 to 5 of 1/2 times 3 to the n minus 1. So what this means is they want you to take the formula 1/2 times 3 to the n minus 1, and they want you to start with the number 1 and continue that formula with integers. So instead of substituting in 1 for n, now I'm going to substitute in 2. And I'm going to keep doing this until I get all the way to substituting a 5 in. Plus 1/2 times 3 to the 4 minus 1 plus 1/2 times 3 to the 5 minus 1. Okay, so I could typo this all into my calculator, or I have a couple of options. The other one is to use the sum formula, substitute in there, or also just grab a calculator and enter this. So we're going to start by practicing that sum formula, which is S sub n equals A1 times, actually no we're not, because it's going to take a lot more work. So instead, practicing the sum formula, we're going to just evaluate this in Desmos, because it's important that you know what it means, but then you also need to be able to evaluate it. So in Desmos, if you type in the word sum, that option will pop up, or you can go into functions, and it's in here under miscellaneous. Click that option, it'll pop up. And I'm going to go from n equals 1 until 5 of, and then make sure you put the whole thing in parentheses. So 1/2 times 3 to the n minus 1. And I need to put that n minus 1 in parentheses so it's all in the exponent. And that's 60.5. All right, so in example 5, we are asked how many terms are in this series. So I have the first term, I have the last term, and I want to know how many terms there are. So I could continue the pattern and fill in the blanks and just count, or I can use this information right here and figure out how many terms are in the series. So if I can solve for n, which would be the number of the term, because I want to know if 768 is the last term, then I want to know how many terms there are to get that 78. So I can use what I know. I know the last term is 768. I know the first term is 3. The common ratio, I'm looking at what I have to multiply to get the next term. 3 times 2 is 6. 6 times 2 is 12. So R is going to be 2 to the n minus 1. And now I have an exponential equation. So we'll use our skills from last class to figure out how to solve. So first, divide both sides by 3 because we want to isolate that exponential expression. So 768 divided by 3 is 256. So now I have 256 equals 2 to the n minus 1. Now, if I have this, might be nice to just change to log form. So I can say that this is log base 2 of 256 equals n minus 1. Then all I have to do is add 1 to both sides, but make sure you're not adding to the 256, add it to the front, because you have to take the log base 2 of 256 before you can add it to 1. So 1 plus log base 2 of 256 equals n. Then I'll grab my calculator, I'll type that in, and I'll have how many terms there are. So 1 plus log base 2 of 256. I get 9. There's 9 terms. So there are 9 terms. And then in part B, this time they give me the sum. So now is here when I want to use my sum formula. So S sub n equals A1 times 1 minus R to the n over 1 minus R. So it tells me the sum of the series is 155. So S sub n equals 155. The first term of the series is 5, so I know A1 is 5. The common ratio is 2. How many terms are in the series? So we need to figure out what n is. So I'm going to substitute what I know into my formula. 155 equals 5 times 1 minus 2 to the n over 1 minus 2. And then I can simplify. Now I can't combine this 1 and 2 because order of operations says you raise the 2 to the n, then subtract it from 1, but I can subtract here. 1 minus 2 is negative 1. So then I'm going to try to isolate this 2 to the n. So it looks like I can multiply both sides by negative 1. So negative 155 equals 5 times 1 minus 2 to the n. Divide both sides by 5. Negative 31 equals 1 minus 2 to the n power. I can subtract 1 on both sides. Negative 32 equals negative 2 to the n. And before I start changing this into logs, I'm going to make sure this term is positive. So divide both sides by negative 1. 32 equals 2 to the n. But then I say, hey, wait, I know 2 to the 5th. This is just from remembering 2 to the 5th is 32. Or if you can't remember that, I can say log base 2 of 32 equals n, and you'll find that n equals 5. So how many terms are in the series? There are 5 terms in the series.